Polyvinyl chloride, more correctly but unusually poly, commonly abbreviated PVC, is the third most widely produced synthetic plastic polymer. After polyethylene and polypropylene, PVC comes in two basic forms: rigid and flexible. The rigid form of PVC is used in construction for pipe and in profile applications such as doors and windows. It is also used for bottles, other non-food packaging, and cards. It can be made softer and more flexible by the addition of plasticizers, the most widely used being phthalates. In this form, it is also used in plumbing, electrical cable insulation, imitation leather, signage, inflatable products, and many applications where it replaces rubber. Pure poly is a white brittle solid. It is insoluble in alcohol but slightly soluble in tetrahydrofuran. Discovery: PVC was accidentally synthesized in 1872 by German chemist Eugen Baumann. The polymer appeared as a white solid inside a flask of vinyl chloride that had been left exposed to sunlight. In the early 20th century, the Russian chemist Ivan Ostromislansky and Fritz Klasser of the German chemical company Griesheim Electron both attempted to use PVC in commercial products, but difficulties in processing the rigid, sometimes brittle polymer thwarted their efforts. Waldo Seaman and the B.F. Goodrich Company developed a method in 1926 to plasticize PVC by blending it with various additives. The result was a more flexible and more easily processed material that soon achieved widespread commercial use. Production: polyvinyl chloride is produced by polymerization of the vinyl chloride monomer, as shown. About 80% of production involves suspension polymerization. Emulsion polymerization accounts for about 12% and bulk polymerization accounts for 8%. Suspension polymerizations are forged particles with average diameters of 100 to 180 micrometers, whereas emulsion polymerization gives much smaller particles of average size around 0.2 micrometers. VCM and water are introduced into the reactor and a polymerization initiator, along with other additives. The reaction vessel is pressure-tight to contain the VCM. The contents of the reaction vessel are continually mixed to maintain the suspension and ensure a uniform particle size of the PVC resin. The reaction is exothermic, and thus requires cooling. As the volume is reduced during the reaction, water is continually added to the mixture to maintain the suspension. The polymerization of VCM is started by compounds called initiators that are mixed into the droplets. These compounds break down to start the radical chain reaction. Typical initiators include dioctanoyl peroxide and dicetyl peroxide dicarbonate, both of which have fragile OO bonds. Some initiators start the reaction rapidly but decay quickly, and other initiators have the opposite effect. A combination of two different initiators is often used to give a uniform rate of polymerization. After the polymer has grown by about 10x, the short polymer precipitates inside the droplet of VCM, and polymerization continues with the precipitated, solvent-swollen particles. The average molecular weights of commercial polymers range from 100,000 to 200,000 and the average molecular weights range from 45,000 to 64,000. Once the reaction has run its course, the resulting PVC slurry is degassed and stripped to remove excess VCM, which is recycled. The polymer is then passed through a centrifuge to remove water. The slurry is further dried in a hot air bed, and the resulting powder sieved before storage or pelletization. Normally, the resulting PVC has a VCM content of less than 1 part per million. Other production processes, such as microsuspension polymerization and emulsion polymerization, produce PVC with smaller particle sizes with slightly different properties and with somewhat different sets of applications. Microstructure: the polymers are linear and are strong. The monomers are mainly arranged head to tail, meaning that there are chlorides on alternating carbon centers. PVC has mainly an atactic stereochemistry, which means that the relative stereochemistry of the chloride centers around him. Some degree of syndiotacticity of the chain gives a few percent crystallinity that is influential on the properties of the material. About 57% of the mass of PVC is chlorine. The presence of chloride groups gives the polymer very different properties from the structurally related material polyethylene. Additives to finished polymer. The product of the polymerization process is unmodified PVC. Before PVC can be made into finished products, it always requires conversion into a compound by the incorporation of additives such as heat stabilizers, UV stabilizers, plasticizers, processing aids, impact modifiers, thermal modifiers, fillers, flame retardants, biocides, blowing agents and smoke suppressors, and, optionally, pigments. The choice of additives used for the PVC finished product is controlled by the cost-performance requirements of the end-use specification, e.g., underground pipe, window frames, intravenous tubing, and flooring all have very different ingredients to suit their performance requirements. Previously, polychlorinated biphenyls were added to certain PVC products as flame retardants and stabilizers. Phthalate plasticizers. Most vinyl products contain plasticizers which dramatically improve their performance characteristic. The most common plasticizers are derivatives of phthalic acid. The materials are selected on their compatibility with the polymer, low volatility levels, and cost. These materials are usually oily, colorless substances that mix well with the PVC particles. About 90% of the plasticizer market, estimated to be millions of tons per year worldwide, is dedicated to PVC. High and low molecular weight phthalates. Phthalates can be divided into three groups based on their molecular weight. Low molecular weight phthalates have 6 or 7 carbon atoms in their alcohol chain. Medium molecular weight phthalates have 8 or 9 carbons in their alcohol chain. High molecular weight phthalates have from 10 to 13 carbons in their alcohol chain. Low molecular weight phthalates are no longer used in the US because of high volatility at PVC processing temperatures. The most common medium molecular weight phthalates are DOP and DINP. High molecular weight phthalates have a limit of 12 carbons or 13 carbons in the alcohol chain because phthalates with longer alcohol chains are incompatible with PVC resin. The more common high molecular weight phthalates are DIDP, DPHP and DTDP, all from branched alcohols. There are phthalates from linear alcohols from 8 to 12 carbons which are used when the flexible PVC compound is to have superior low temperature, flexibility and improved weathering. Because of possible health effects, there are movements to replace some phthalates such as DOP, DEHP with safer alternatives in Canada, the European Union, and the United States. In Europe, DEHP and DBP are undergoing the REACH authorization process. Registration, evaluation, authorization and restriction of chemicals with results expected in 2014. Since no applications for BBP and DIBP were received by the European Chemicals Agency, the use of these substances will be phased out in the EU by the 21st of February 2015. Mid-high molecular weight phthalates today represent over 85% of all the phthalates currently being produced in Europe. On the 31st of January 2014, the European Commission published its conclusions regarding the re-evaluation of the restrictions on DINP and DIDP in toys and child care articles which can be placed in the mouth. The Commission confirmed the main conclusions presented in August last year by the ECHA, which was asked in September 2009 to review any newly available scientific information relative to these two high phthalates. The European Commission concluded that no unacceptable risk has been characterized for the uses of DINP and DIDP in articles other than toys and child care articles which can be placed in the mouth. With regard to the latter, the existent restrictions are nevertheless maintained, based on the precautionary principle. DINP and DIDP are therefore safe for use in all current consumer applications. The European Chemicals Agency also concluded that no further risk management measures are needed to reduce the exposure of adults and children to DINP and DIDP. Heat stabilizers. One of the most crucial additives are heat stabilizers. These agents minimize loss of hydrogen chloride, a degradation process that starts above 70 degrees Celsius. Once dehydrochlorination starts, it is autocatalytic. Many diverse agents have been used, including, traditionally, derivatives of heavy metals. Increasingly, metallic soaps are favored, species such as calcium stearate. Addition levels vary, typically from 2% to 4%. The choice of the best heat stabilizer depends on its cost-effectiveness in the end-use application, performance specification requirements, processing technology and regulatory approvals. Rigid PVC applications. Regular PVC is a common, strong but lightweight plastic used in construction. It is made softer and more flexible by the addition of plasticizers. If no plasticizers are added, it is known as UPVC, rigid PVC, or vinyl siding in the US. In Europe, particularly Belgium, there has been a commitment to eliminate the use of cadmium and phase out lead-based heat stabilizers such as liquid autodiachromate and calcium polyhydrochromate by 2015. According to the final report of Vinyl 2010, cadmium was eliminated across Europe by 2007. The progressive substitution of lead-based stabilizers is also confirmed in the same document, showing a reduction of 75% since 2000 and ongoing. This is confirmed by the corresponding growth in calcium-based stabilizers, used as an alternative to lead-based stabilizers, more and more. Also outside Europe, tin-based stabilizers are mainly used in Europe for rigid, transparent applications due to the high-temperature processing conditions used. The situation in North America is different, where tin systems are used for almost all rigid PVC applications. Tin stabilizers can be divided into two main groups. The first group containing those with tin oxygen bonds and the second group with tin sulfur bonds. According to the European stabilizer producers, most organotin stabilizers have already been successfully REACH-registered. More chemical and use information is also available on this site. Flexible PVC applications. Flexible PVC coated wire and cable for electrical use has traditionally been stabilized with lead, but these are being replaced, as in the rigid area, with calcium-based systems. Liquid mixed metal stabilizers are used in several PVC flexible applications such as calendered films, extruded profiles, injection molded soles in footwear, extruded hoses and plastisoles where PVC paste is spread onto a backing. Liquid mixed metal stabilizer systems are primarily based on barium, zinc and calcium carboxylates. In general, liquid mixed metals like BAS, CAZN require the addition of co-stabilizers, antioxidants and organophosphites to provide optimum performance. BAS stabilizers have successfully replaced cadmium-based stabilizers in Europe in many PVC semi-rigid and flexible applications according to the European producers. Physical properties. PVC is a thermoplastic polymer. Its properties are usually categorized based on rigid and flexible PVCs. Mechanical properties. PVC has high hardness and mechanical properties. The mechanical properties enhance with the molecular weight increasing but decrease with the temperature increasing. The mechanical properties of rigid PVC are very good. The elastic modulus can reach 1,500 to 3,000 megapascals. The soft PVC elastic is 1.5-15 MPa. Thermal and fire properties. The heat stability of raw PVC is very poor, so the addition of a heat stabilizer during the process is necessary in order to ensure the product's properties. PVC starts to decompose when the temperature reaches 140 degrees Celsius, with melting temperature starting around 160 degrees Celsius. The linear expansion coefficient of rigid PVC is small and has good flame retardancy, the limiting oxygen index being up to 45 or more. The LOI is the minimum concentration of oxygen, expressed as a percentage, that will support combustion of a polymer, and noting that air has 20% content of oxygen. Electrical properties: PVC is a polymer with good insulation properties. Because of its higher polar nature, the electrical insulating property is inferior to non-polar polymers such as polyethylene and polypropylene. Since the dielectric constant, dielectric loss tangent value, and volume resistivity are high, the corona resistance is not very good, and it is generally suitable for medium or low voltage and low frequency insulation materials.